So the format will be that I'll begin the talk, and after a few slides, Henrique will take over and make up for my mistakes en route. So we'll see how we go. So this is work in progress, arising from ideas, mostly Henrique's. For me, it's been returning to a topic that I used to work on. And of course, the whole argument is one of the great crossroads of the history and the philosophy of relativity theory. And so it's a very rich field, and it's got many aspects that researchers young and old can take some pleasure in. So what does it do? Well, the whole argument was originally invented by Einstein in 1913, on the way to general relativity being formulated, was revived in the 1980s by Stachel, Norton, and Ehrman. And we're going to look at entirely the modern post-1980s version, in which the whole argument, in effect, is saying, if you believe in space-time points being objects, then you are confronted in a theory like general relativity with a radical indeterminism. And when Ehrman and Norton, building on Stachel, pushed this argument, they pushed it as you shouldn't have such a radical indeterminism, so you shouldn't believe in space-time points. And substantivalism, the belief that space-time points are objects, therefore has a decisive objection against it. Now, the most common reply to this is to say that actually the way you individuate points as objects is by the pattern of properties and relations they enjoy, and that when you do that carefully, there will not be an indeterminism. And we make this a bit more precise with the following label. It's going to be called the drag-along response. This is our word, but it's widespread in the literature, this idea that if you're given an isomorphism from one space-time model to another that sends a point little p to a point little q, then p and q correspond in some intuitive sense of correspond. And the idea is it's only if there is such an isomorphism that p and q can correspond. And speaking more philosophically, a bit more substantially and more vividly, the drag-along response says you really should take Q as really being P when they are related by an isomorphism. You should replace Q with P. And in a paper 3 years ago, British Journal of Philosophy of Science, Weatherall argued that this response is actually mandated, it's compulsory from the maths of general relativity. And our talk is going to reject Weatherall's claim, but we do agree that the maths is indifferent, meaning doesn't care about the identity of points. And that's true about maths in general, the so-called structural practice. The structuralist way of going on in modern mathematics is to be interested in pattern or structure, but not care about what are the objects that instantiate the pattern or the structure. So we agree that modern mathematics is indifferent, and it's indifferent in general relativity to the points in the formal models of general relativity, or indeed other space-time theories. So the drag-along response is in that sense natural. But we say, this is the last part of our intro, that the response is actually limited, because this is the more positive thing. We're going to disagree with Weatherall about the drag along response being mandatory, but then we're going to be saying more positively, there is another story that Weatherall and the literature has missed, namely general relativity and other space-time theories use other means of trans-world identification, not just by isomorphism. And we call it threading, like when you're doing sewing. And there are various examples. And the other thing we're going to end on is emphasizing that if you have a symmetric model, then the drag along response, at least in a simple version, has trouble. And also, there's a subtlety about what a substantivalist should say. Namely, they have to be a bit careful about region versus cosmos. What they say about the whole cosmos versus what they say about a region. So the plan is that we'll talk about the whole argument and the drag along response. And then we're going to, in section 2, talk about the limits of drag along, which will be showing how the practice of our geometry and the practice of our space-time theories invokes other ways of making points correspond or get associated across one model and another. And then that will raise the question, oh, well, what exactly is the scope of validity of the drag along? And I think they call this in America a spoiler alert, which is where you prevent anticlimax later by admitting that you don't have a good answer. So please don't be hopeful. So the spoiler alert is we don't have a general clever philosophy formulation of under what conditions is drag along right. And we suspect there isn't one, because the practice of geometry and space-time physics is so varied, but we can certainly find you some examples where drag along isn't occurring. And of course, it sometimes does look sensible, right? That's a very neutral statement, but I think it does reflect the variety of practice. Of course, different authors will have different, what you might call intellectual temperaments about how willing they are to do straight up metaphysics or straight up philosophy of modality or straight up speculation about how to think about objects across all possible worlds. And, people differ about this. And of course, I tend to be quite metaphysical, and Weatherall is clearly anti-metaphysical. But there's certain things that I think different authors with different temperaments would agree on. And one is we want to urge everybody should recognize there is this variety of practice in geometry and space-time physics about association or identification of points across models. Okay, so here's the great John Norton drawing a lovely picture to illustrate the whole argument. And basically, the picture in here is that you take an isomorphism between two models that have got the same manifold, so they've got the same base set of space-time points. And if you look at this, what you might call naively, which for me is always a positive word, though in English language it tends to have the negative connotation. But I always like to be naive, because at least you're not in a muddle, right? So let's be naive. It looks like you have two different distributions of spatiotemporal relations encoded by the metric, and different distributions of material properties and relations, which are going to be encoded by things like electromagnetic field. And it's two different such distributions over one and the same base manifold, right? And in this example, says Norton, question, does the galaxy pass through space-time point E? On the face of it, it does not on the right, but it does on the left. And the philosophical and so far vague idea about how to reply to this indeterminism is, but points are really individuated by their pattern of properties and relations encoded in these fields. So once you're given an isomorphism, F, which sends a point P to a point Q, only once that is given do the points really correspond. And the two pictures are really representing a single physical possibility, and they seem to represent different possibilities because you have used the page, the white paper in the background, to name a piece of paper called E. But that's just an artifact of using paper. The space-time point got dragged along with the curve. And on the right-hand picture, the space-time point labeled E on the left should also be lying on the bent curve on the right. Okay, so that's a drag along response. And the older jargon is to call this anti-hexutism or sophisticated substantivalism. And Pooley, in his excellent review, which we'd recommend in that new Routledge handbook, it's on Pittsburgh for September 2020, calls it denying that the two models represent different possibilities, or denying plurality. Okay, so we are going to say that's okay up to a point, but it's limited. And the first comment is not caring about alpha, some topic, is not the same thing as one practice concerning alpha being mandatory. If you don't care about something, that doesn't mean only one way of treating the topic is mandatory. Now, mathematics is indifferent to the identity of its objects, and we could even discuss the famous Frege-Hilbert controversy in that connection. But that doesn't mean it's mandatory to use drag along for the transworld identification. Our point is that maths is really flexible. It's even opportunistic. It takes objects as the same or as corresponding to each other in whatever manner it needs for the project that it is currently undertaking. And this happens in differential geometry, quite apart from space-time physics. And we want to suggest an umbrella term for these other means, and we use it threading. So the idea is that you've got a linkage, so you have threaded 2 points together. There's a thread between them. But we're not got some single notion of threading. We think different threading relations get invoked in different parts of our mathematical practice. So philosophical comment, individuate is a very philosophical word. Identification is also a rather philosophical word. They are often meant in philosophy to signal what a philosopher would call fully fledged identity, the equal sign. But for us, it doesn't mean that. When we say that points are individuated by their space-time points or something like that, that just means something like they might be counterparts, for example, in a modal metaphysical counterpart theory. But individuate does otherwise for us have the meaning that it has in philosophy, that it's all about finding a weak sufficient condition for a statement of correspondence, identification. Weak because tractable. And here's the example in general philosophy. People say, persons are individuated by their bodies. What does it mean when we have to teach that in, metaphysics or philosophy of mind class? What it means is something like, having the same body implies being the same person. That is, being the same object. And that, by Leibniz's law, namely, if x equals y, then all the properties of x and of y are shared. If x equals y, then x and y share all properties whatsoever. That's not Leibniz's principle of the identity of indiscernibles. That is the controversial converse implication. Leibniz's law really is a law. It's like if x and y are names of the same thing, then there's only one thing. And so, of course, the properties match, right? So anyway, the point of a claim that having the same body implies being the same person is to give a sufficient condition for identity that is usable, tractable in a way that Leibniz's law clearly is not. It's far easier to check that two objects are the same body than to check that they match on all properties whatsoever, okay? Find the same body and you will have found the same person. That's the idea of individuate. Okay, so at this point, I'm going to hand over to Henrique, who will actually now get into the detail.
Thanks, yeah. Do you want me to try to include the screen?
Yeah, a little bit. I'll leave him.
Right. Okay, so thank you, Jeremy. The first example in geometry that we clearly need to invoke threading is when we use the Lie derivative. So, in fact, there are various contexts within differential geometry, and in which this flexible treatment of the identity, which Jeremy was mentioning, is very clear. So we need to take facts about identity in its stride, as mathematics does, and acknowledge that such treatments are not Higgsistic or Higgsatist, and they're not committed to a stronger philosophical claim that's sometimes identified with Kripke, that any transworld identity can be stipulated. As Jeremy was saying, this is rather the fact that mathematics is entirely indifferent to identity. And when usually in most textbooks, when we define the Lie derivative of a field, you imagine a flow, a diffeomorphism of some sort, dragging the field along along the flow lines over some points that are fixed underneath this dragging. And when you take this infinitesimal, the infinitesimal quantities as they vary through this flow, that is the definition of the Lie derivative. And clearly this means that we appeal to some identity or correspondence of points, so that the sliding of the field along the curve through the points makes sense. We need to keep the points fixed if anything is going to slide over them. Otherwise, everything would slide together. So Arnold has this very, I found somehow very representative of my idea of Russian mathematicians and physicists of this era, at least. He says that the Lie derivative is sometimes called the fisherman's derivative, because one can think of the integral curves of the vector field as the flow lines of a fluid, e.g. a river, and then he somehow completely mixes up the metaphor and says that the flow carries all possible differential geometric objects past the fisherman, and the fisherman sits there and differentiates them. But so that's the idea, right? Is that not that the fisherman is differentiating geometrical objects, but that there is a flow when something just sits there and sees how this things that are being carried by the flow are changing. And so, of course, here the stationarity of the riverbed is the analog of the fixed points over which the fields slide. And but according to the drag along, the field cannot be dragged with respect to the points of the manifold, because we are re-identifying, relabeling the points by the diffeomorphisms that is also being used to drag the fields. And if you insert this idea in the standard definition of the Lie derivative, here you see that we're also writing some flow for the points themselves. They're being dragged along by the same diffeomorphism as being used to drag the fields here, the pullback of G. And this is identically zero, because you just move the metric and the fields back and forth to the same point, and it's identically equal to the first element. One should note here that there's no uniform meaning to this assumed identity of points that the Lie derivative presupposes, and one doesn't need to invoke such a meaning. All that matters for the definition of the Lie derivative is that there's some other meaning besides the drag along. I should briefly note here that there are different definitions of the Lie derivative that are more algebraic, that give you axioms about how it's going to be, how it's a derivative operator and so on, how it acts, how it commutes with the exterior derivative, how it commutes with contraction, and so on. And one could say that that does not require this idea, but one would lose a lot of the uses and the intuition of the Lie derivative in the practice of differential geometry. For instance, its relation to flow lines, and it's not the standard way of defining the derivative. So right, so here what matters is that differential geometry endemically invokes a scheme of identification other than drag along. And as Jeremy mentioned, we call this a threading scheme. And 2 points are threaded to each other. They are related by a threading, one in the domain and one in the range of the diffeomorphism. And to emphasize yet again, we have an indefinite article. We call it a threading relation. No, not the threading relation. And here's an example where we use Lie derivatives to do differential geometry. When we define in relativity theory of rigid continuous body, or a body for whose for velocity of its material particles Lie drags the metric, then we need to say that that is rigid if this condition holds. So the Lie derivative of the metric along those flow lines vanishes. The metric does not change along those directions. It's rigid in this way. And conversely, to describe the motion of non-rigid continuous body, we need a definition whereby the Lie derivative of the metric is not zero. And so with drag along, since everything in this definition would be since for all vector fields using the drag along, one would have the Lie derivative as defined by infinitesimal flow be zero, then a drag along cannot be used jointly with the Lie derivative to find the killing fields of the metric, or the rigid isometries of the metric. And there are much more sophisticated examples. So here one could say, well, this has nothing to do with the symmetries of GR, say that what you're describing to me may be true, but it has nothing to do with the symmetries of GR. But then we can invoke an application of these ideas to Noether's theorems, in particular to Noether's second theorem, which is a statement about the symmetries of GR. And here is a very quick derivation of this theorem. You have an action, sorry, this is supposed to be a D and not a delta, an action of the two Lagrangian densities. One is geometric and the other includes matter. And we vary this action along a vector field that is generator of a diffeomorphism. So a symmetry of the Lagrangian, and that's what we would usually identify as a symmetry. And if supposing this vector field or this flow has compact support, it's the identity outside of a compact set, the boundary terms would vanish. And then if you just do the computation, again, this is a D, it's some wrong tech code. And what you do here is you take the variations of the two Lagrangian densities with respect to the metric, you contract with the variation of the metric in the direction or along the infinitesimal flow, and you get the Einstein tensor and the energy momentum tensor. These are the definitions, and it's again, we're ignoring boundary terms, and this is contracted with the variation of the metric infinitesimal. If you were employing here the drag along response, you would always get 0 for this. You would get no meaningful or interesting identity. So here we see that you have to identify the type of flow that is generated by diffeomorphisms seen as symmetries of the Lagrangian with a transworld identification that is not the drag along, that is threading. So to sum it up here, we need to use threading to deal with the symmetries of GR if we are going to derive any non-trivial consequences from another second theorem. Yes, so here, I'm sorry, yes. And the non-trivial consequence that you get from this is that if you write down here LXJB as the covariant, symmetrized covariant derivative of the vector field, and you then integrate by parts here. So here you have nabla A XB symmetrized, and you integrate by parts, you get a covariant derivative of these two terms equals 0, because this variation is equal to 0, and we have no boundary terms. And therefore, it gives you this identity here, 4. Of course, then using the Bianchi identity, we have this side is 0, and so we also get that the right-hand side is 0. So note here that we didn't explicitly use the Einstein equations. This conclusion here is valid. It arises solely from the statement that the action is invariant under these types of symmetries. All you do is vary the action and get this term here and do integration by parts and then use the Bianchi identity. In fact, I mean, this would allow, for example, that JB is not just JB, but has something else, as long as that something else was covariant, was divergenceless, covariantly divergenceless. So it's important to note here that this does not, we're not claiming that the drag along response implies that energy is not locally conserved. Of course not. But it implies that the proof of conservation of energy using the drag along cannot go via another second theorem. You would need to resort to other techniques and yeah, other ideas. There is a second use of this type of threading, and this is a bit more sophisticated, and it also renders this difference from dragging along more vivid. In this example, we imagine metrics that are not related by isometry. So a one parameter family of spacetimes, which are not isometric to each other. And here they're labeled M lambda and G lambda. And you imagine these you imagine this as a stack of four-dimensional metrics, say. And so it's a five-dimensional manifold M, which is foliated by these four-dimensional metrics and manifolds. And the limit spacetime would correspond to one of these ends of this stacked five-dimensional manifold. And to write down these limits, Gerhardt needs to use curves that cut the leaves. And so they thread together points in non-isometric spacetimes. You're using a notion of identifying points across spacetime. And in fact, there is no drag along available for you to use because there is no isometry between these leaves. So you need to invoke some other notion, and it can be pretty arbitrary. Right. Eric Curio also has something about this in his BJPS 2018 paper. So here's a summary of the main story so far, as we see it. All hands agree that general relativity does not care about which points instantiate which properties, or about the difference in transworld identities between points of its models manifolds. However, I think it goes too far to say that this settles interpretative metaphysical issues. And this is, in fact, a quote from Pooley regarding Weatherall and Fletcher, who also has a paper responding to Weatherall's whole argument paper. Both authors argue that if there are pluralities of merely hagiatistically distinct possibilities, the mathematical formalism of GR, correctly interpreted, is necessarily indifferent to differences between them. But this just means that GR does not distinguish between any two elements of such a plurality. Both will count as physically possible according to GR, or neither will. And that, of course, is just to admit that according to any metaphysical view committed to such pluralities, GR is indeterministic. The indeterminism cannot be avoided by remaining loftily above the metaphysical affray. And there's a largely, sadly, neglected paper by Arledge and Ranajevich, which has very similar ideas, sections 3 and 4. So here we face this question that Jeremy already spoiled at the beginning, who already gave away the negative answer to at the beginning of the talk. When precisely is drag along the correct, or at least an appropriate scheme for identifying points? And the truth is, we have no general answer, and perhaps there is no general answer, even if you assume other facts about metaphysics of modality and so on. But there's a lot of interesting inroads to what this general answer may be. So, and lots of interesting questions to explore using this contrast between the drag along and the threading relation. So one of them, for example, is to note that symmetric models will make trouble for the drag along response. And the second thing that we take this contrast sheds light on is about interpretation of regions according to the substantivalist. And the idea or the conclusion from this application is that the substantivalist should not interpret too hagiatistically two regions whose points are related by threading. So let's see the first one, what comes about. So you suppose that there are two or more isomorphisms now from a model M1 to a model M2, and the diffeomorphism or the isomorphism F1 maps a point P, say in M1, to Q1 in M2, or sorry, Q1 or Q2, to Q1 and Q2 in M2, where Q1 is different than Q2. So the model M2 has a symmetry now, where you use F2. So sorry, here is not what Fi means that this I is the same as this I. So F1 will map a point P to point Q1 in M1, and F2 will map that same point P to a different point Q2 in M2, and Q2 is different than Q1, right? So we have two isomorphisms, and they take a point P to two different points. And since they are both isomorphisms, the model M2 will have a symmetry, which is just this composition here. It goes from M2 to M2, and it's an automorphism of the model. And the drag along will face a contradiction, because both Q1 and Q2 have now been dragged along or identified with P. So which one is it to be? And this type of difficulty arises for any symmetric model. And it was propounded, consequences of this argument were propounded as an abysmal embarrassment refuting structuralism by Chris Wothrich in a paper in 2008. And Muller has a reply, which I endorse. I think Jeremy does as well. Replies that structuralism escapes by allowing points to differ. Solo numero. Agreed, but it's still true that the drag along response needs to be refined in this case, even if Muller is correct. He does not invoke the drag along for his response, and I don't see. I definitely see some tension in the drag along response and the existence of symmetric models. And the second idea. So since we have a little bit of time, maybe I can go off piste here, of course, and just say a little bit more about this symmetric models, because there is a more recent paper by Halverson and Manchak, and they see the threat of the whole argument as arising solely from these kinds of isomorphisms from or symmetries, automorphisms of symmetric models, let's say. So they think of, for instance, the Poincaré transformations of a Minkowski metric. That's the kind of general type of symmetry or transformation that they're concerned about. And that, of course, and they invoke another theorem of Garrock, not the ones we have been talking about here, to say that these types of isomorphisms do not threaten indeterminism, and that's correct. That type of isomorphism is rigid, so once you determine it in any sub open region of the manifold, it's determined everywhere else. So there's no, if you perturb it initially, it's perturbed at every moment, and so there's no threat to indeterminism. But we are saying here that this is not the original argument, or the original threat of isomorphisms did not arise solely from these types of rigid symmetries of the manifold. They arose from general automorphisms. And there is then this tension about, if you're going to endorse the drag along, about what you're going to do with the symmetric models. And I think the response by Manchak and Halverson is it only it cannot combine these two answers, the answer by the drag along and the answer that they provide, because the drag along is in tension with symmetric models. Okay, now returning to the standards track. The second point that I wanted to make, that we wanted to make in the applications of threading and in contrast to the drag along, is about a warning to the substantivalist. And the warning is that they should not interpret threaded regions too exotistically. So here, suppose that 2 points lie in isomorphic models. And so the two models are isometric as well. And these 2 points are threaded. But they're threaded not by the isomorphism, they're threaded by a contrasting notion. And say that, you know, we just are using whatever notion of identity we had. So we're saying that these two subsets in these two models are just labeled by a region called U. So we're saying U in this model is U in this other model, because we're helping ourselves to this notion of threading, right? So we have identified these two subsets in the base set manifold. Now, in these two models, you can think that G and G prime are isometric. So there is some other isomorphism, some other diffeomorphism that will pull back G to G prime, or vice versa. And this will happen globally, right? So G and will be pulled. So there is a diffeomorphism, which is a bijective smooth function with a smooth inverse that will bring G prime back to G on the whole manifold. But still, it's not true that G restricted to U and G prime restricted to the subset are going to be physically the same. They will be physically distinct. So G and G prime restricted to U might ascribe different properties to this subset. So for example, G will ascribe a volume V to U, and G prime will ascribe it V prime. And V prime is different than V. And similarly for other fields and other objects. So in the two models, thoroughly different functions have support in U. So here, I would like to say the sophisticated substantivalists can only say that G and G prime are the same, or represent the same possibility, if they are countenancing the entire manifold. If you were to restrict yourself to any region, then they wouldn't be physically the same. So G and G prime really do differ physically on subregions. And so a substantivalist who wants you to be the same region in the two models cannot be sophisticated. That is, she must accept physical differences between isomorphic models. And to be sophisticated, she must confine herself to entire manifold statements that do not specify where and when, for instance, in U or not, a field value is attained. Okay, so now we're reaching the conclusion, and we think it's we think it's fair to say that all hands agree that the mathematics of general relativity doesn't care about which points instantiate which properties. But we think that this doesn't settle interpretative or metaphysical issues. More specifically, the drag-along response is not mathematically mandatory, and it is also limited. General relativity and other space-time theories endemically use other means of transworld identification of points. And here we presented 3 examples: Lie derivative, Noether's theorems, and limits of spacetimes. And a contrasting threading scheme must also be careful about interpreting the threaded regions. Isomorphic models will have physically different regional properties, but no physical difference for the entire manifold. All right, thank you.
So my question is, can you, in some sense, generalize your threading approach to the Newtonian case with, you know, the static and kinematic shifts? Is there a way this kind of change in description can be useful also in addressing this kind of arguments?
Do you want to go first?
Go for it.
Thank you. Yes. So, am I right? The static shift is a spatial translation.
Yes.
And the kinematic is a boost. Yeah.
Yep.
And so it is true that in both cases we have an isometry. We have an isomorphism of space-time structure. And I don't see any, I think we could say in our language, what are the options? I know there's a debate about, in the more, you know, Pooley and others, recent literature about contrasting static and kinematic, but I have to admit I can't quite remember it now. But one can imagine talking about spatial translation and boosts in our language, saying, oh, well, the person who wishes to deny, like Leibniz wanted to deny, that a spatial translation produces a new case, such a person will say, we should do drag along. And they might even be called Jim Leibniz and say, I live in Irvine and I can show it's mathematically mandatory to have only one case. And I certainly philosophically would want to say, no, dear Jim Leibniz, it's not mathematically mandatory to identify. So although we said nothing about it, we believe, I'm sure I speak for Henrique as well, that in elementary cases also we don't have mathematically mandatory drag along. And I would wish to say the same about the boost. So apart from the modern sophisticated controversies, Pooley and others, this would be my first comment about it. But Henrique, you want to add?
I mean, one could, it sidesteps the question a little bit, but if you use Newton-Cartan theory, then the formalisms are much more similar, and you can essentially apply the same ideas. There is a little subtlety here, which is the one we mentioned in the talk, about these sort of automorphisms of the structure and play. So, for instance, when you have killing symmetries and so on. And I would have to think more carefully about whether you would find the same sort of obstacles for these symmetries of the Newtonian case, which are also rigid. So that could be a snag there.
Okay, thank you. Tomasz has a question. Please, Tomasz, go ahead.
Okay, hi. Thank you, Jeremy and Enrique, for this lovely talk. I really enjoyed it. I think it made me think a lot about different things, but for the time being, let me just focus on two things. I mean, one short comment is I really like the idea this expression that mathematics doesn't care about identity. But I would put it slightly differently. I would say that in mathematics, it's entirely up to us to decide which points are identical or which objects are identical. So like we decide what, which sort of identity we should follow. But with physics, things are a little bit more intricate. So with physics, we have to keep in mind things like empirical distinguishability and that sort of thing. So I think that in physics things are a little bit more intricate. So that's kind of like one small comment. And I also have another little comment on this abysmal embarrassments argument by Chris Wittrich. It seems to me, I don't know if you would agree or not, it seems to me that the argument can be easily repelled if we follow David Lewis's counterpart theory. Because in this theory, there's nothing wrong with saying that a particular point can have more than one counterpart in a possible world. So the fact that you have two or more isomorphisms, I mean, it doesn't spoil anything, because the counterpart relation is not identity, so it doesn't have to be one-to-one. So yeah, so these are my comments. Thank you anyway. Thank you.
Well, Thomas, I'm going to go first because you and we're the philosophers here, and the Polish tradition of logic I want it to flow more in my veins. So thank you for the comment about counterpart theory. So I would pick up on, I like both of what things you say. As you happen to know, I like counterparts too. And I agree that in one of these very symmetric space-times, there'll be continuously many equally good candidates for being corresponding to a point in some other model. And that is put by us philosophers as continuously many equally good counterparts of the point in the other model. So I completely agree with what you say. But and I also would just hand over to Henrique if you want to talk more about that, or about the concept of identity in physics, because the first part of Thomas is.
I mean, I have a lot to say about these two things. I'll try to keep it short. I agree. I think if you wanted to identify points physically, then you should invoke, for example, the fields that are that you can use and so on. And then this still allows you a breadth of choice about how you can identify points in several ways using the fields at your disposal. And but once you have chosen one such way, and there are no automorphisms, so for instance, there are no killing fields and no rigid isometries of the metric, then that completely will fix the identity of the points. You will no longer, you can't apply a diffeomorphism and get a different point, because you're saying, for example, point P is the point where, these contractions of the Riemann tensor acquired this value, this numerical value, and so on. And if you apply a diffeomorphism, you will shift the points together with their label, because you'll be shifting the fields. So this type of physical identification, I think, does kind of endorse the drag-along response, but it puts more meat into it. It doesn't, and I don't think it's a response to the whole argument for two reasons. First is, well, as we said, there are other uses of threading in geometry and general relativity, and there is the problem of isometries, as in Wittrich abysmal embarrassment, that you wouldn't be able to distinguish certain points from their. Sometimes these are called Kretschmann scalars. You wouldn't be able to distinguish points by their physical attributes in these cases. So I think there's still room for threading, even if drag along is very useful and comes up in this type of individuation of points by their physical properties. And the other thing I would say about Wüthrich and Müller is that I think there's an issue here that you see the full set of quantities that are physical or invariant under the notion of isomorphism, the theory. So the full set of quantities that are common to all the isomorphic models outstrips the ones that you would get if you identified all their points by their distinguishability relations, as Wüthrich does. So, for example, I can have the volume of the manifold is, if you suppose the sphere or something like that, the volume of the manifold is common to all the isomorphic models. And yet, if you were to identify all the points, you would obtain a single point, and that has no volume. So clearly, there is something amiss doing this. You're not capturing, when you do this identification, you're not capturing all the quantities that are common to all the isomorphic models. So it does not correspond to the right quotient. So yeah, these are my two comments about your two comments.
Okay, thank you. I know that Carl is waiting for his turn, so I don't want to take up too much time. But just a quick follow up, to your reply, Henrique. I think that it has to be stressed. I mean, we have to be really precise in what world we are talking about various identities. Now, as long as you talk about identities in the same world, in the same sort of real possible world, then of course, I mean, then I think that Chris Wüthrich's argument does not show that we are somehow forced to identify points being in the same possible world as one point, because they may be differentiated not by their properties but by some weakly discerning relations. For instance, like the simplest possible weakly discerning relation is being separated by a non-zero interval, by a non-zero distance, spatial distance, for instance. So, but it's a different thing. This is different from identifications across possible worlds or trans-world identifications, which of course, I mean, yeah. So
absolutely, no, that's yeah. Thank you for that clarification. I really endorse it.
Okay. And other than that, I totally agree with what you have said, both Jeremy and you, Henrique. So thank you again. Very good talk. I really liked it. Thank you.
Thank you.
Thanks, Tomasz. Carl, it's your turn.
Yeah, so I actually wanted to talk about largely the same things, but because the thoughts I have are sparked especially by that place where you were talking about Wüthrich's symmetries argument, and it's interesting. I think, Jeremy, you should remember this, although not Henrique, but that argument was actually really in almost identically the same form given by Ehrman in his 1989 book. And it was given against a way of responding to the whole argument, which he took a primitive, sophisticated person might offer, which was basically, I think, what now Jim Weatherall may be preferring to us by the drag-along identification option. I haven't read Weatherall's paper, but and this shows to me that one should be careful not to identify all of these moves as being essentially the same, because it's one thing to do what I offered back in the day, which was to deny primitive identity to space-time points, or indeed any sort of physical object that you might want to talk about that makes sensible to make these kind of trans-world identifications. And it's a different thing to offer a specific theory of how do you make these trans-world identifications. And if you, what Ehrman was objecting to is a kind of a structural role account of trans-world identity of space-time points, because then when you find you have a symmetric world, and you can get Q1 identical to P, but also Q2 then should be held identical to P in this other world, and then you're in the soup. But if your view is anti-Hexiatist in a strong way, what you just want to say is, look, are these two worlds qualitatively identical? Then they're not representing different metaphysical possibilities at all. They're just mathematically different objects. And that doesn't commit you to making any trans world identifications, because you really only got metaphysically one world. And then you say, oh, but does that mean you're committed to Q1 and Q2 being the same point? Well, no. And for much the reason that Thomas just said, well, they're separated from each other by an interval. So I don't have to say they're the same point, even though they have the same qualitative features. So anyway, I just wanted to make kind of this historical note. And I have read a few papers talking about whole argument things in the past couple of years. And I do find that it's taken on a new life, and people have sort of forgotten a lot of things that people said back in the 1980s, including you and me and John Ehrman. Anyway.
Dear Carl, well, Henrique, shall I go first on this?
Yes.
Yeah, dear Carl, that's extremely helpful to me. Thank you. I actually, to us old guys, soulmates, right? We, as Nick Huggett said on some Zoom session in this sad 18 months we've had, where happily though Zoom brings us close to old friends on the screen, Nick said, oh yeah, it's funny how these issues come back, right? And it's partly in the nature of philosophy that every generation has to conquer the same logical geography, the varieties of free will and its reconciliation with determinism. These are abstract matters that naturally go muddly in your mind, so we have to recover them. And the language in which the distinctions get made or the logical geography gets reported will vary. And I confess, I myself forget, right? I'd really completely forgotten that the Ehrman 89 book may well give the Wootrick abysmal embarrassment argument. But I completely agree with what you say, dear Carl, about the argument there is that a certain kind of structural role specifies trans-world identity is bound to stumble on highly symmetric cases. And or indeed it's going to stumble on symmetric cases, and in particular even a single symmetry would be enough, like in our slide, to deliver for a simple rendition of structural role identification a contradiction that 2 points in one world must be the same because they're both the same as a single point in another world. So I totally resonate with what you've said. And I think what you and Thomas both said about contrast intra versus across world correspondence or identification is also very true, because in particular, intra-world discerning relations like, these symmetric non-reflexive relations of being a meter from, X is a meter from Y, but X is not a meter from itself. That's another big contrast between. Anyway, sorry. Yeah, Enrique, do you want to add to that?
I don't have much to add. I would say that there is a sense that I think you can quotient by these types of symmetries, because the space of fear. So I think there's a confusion often in this discussion. Because we're not just thinking of the manifold, we're thinking of the manifold and some fields on top of it that determine its geometry and so on, its metric. And these are, if you are mathematically a little bit more sophisticated, you'd call these sections of a tensor bundle. And if the points themselves have no individuating feature, you could actually represent the entire tensor bundle in a single point. So you could quotient, say, tensor bundle for M, for a round sphere, by the group of rotations. That would not confine you to a structureless point. You would have in the point the representation of the entire sphere. I think sphere is a bad example, but in a plane, this is very clear. This is just saying that the tangent plane to any point in a plane contains, is isomorphic to the entire plane. So you can quotient the tangent bundle to a plane by the group of translations, and you get, again, a copy of the plane. So I think Wuthering and these other discussions went a little bit too quick. I think you can, if you really think of the tensor bundles as encoding more of this information that is we are helping ourselves to, then you can actually think about how to identify these different points that have the same stuff on top of them, and you will lose nothing. You will just be re-representing the global structure on just a single point, internally to that single point in the tangent bundle to that point.
Okay, sounds good to me.
I'm just riffing with what...
Well, if Antonio can forgive me, I mean, typical me, bad jokes always. A little finger on what Henrique said. I hadn't quite realized this, that yes, of course, there's this old idea that the microcosm encodes the macrocosm that goes back over 2 millennia. And it's like the tangent plane at a point on the Euclidean plane does encode the whole Euclidean plane. So if you decide to, looking at the whole glorious infinite Euclidean plane, you decide to quotient, you get down to a microcosm that actually contains everything you threw away.
Okay. Josh, please go ahead.
Cool. Yeah. Thanks so much for the talk, guys. Really interesting stuff. I think I have a question about one of the claims that was like the final one in the conclusion, which is that the threading examples give us cases where we have isomorphic models, but they're not physically equivalent. And I think so, like, I'm under the impression that a lot of people think that if you have two isomorphic models, that's sufficient for interpreting the models as being physically equivalent. So I guess I'm just interested, like, do you guys view these threading cases as counterexamples to that claim?
They were not physically equivalent on a subset. They were
but
not.
Are the models physically equivalent globally? Like, do they represent the same states of affairs?
Globally, they represent the same universe, yes, but locally they're physically inequivalent.
I guess could you say more about that? I guess I find that sort of scenario metaphysically puzzling.
Well, if Henrique will forgive me, I can try, because he's a very forgiving person. So he has these ideas, and then pedestrian Butterfield has to ask him to explain it better. So here's how I understand Guru Gomes. It is very, the reason one stumbles on the doctrine is that it's very natural to regard a global statement as a conjunction of local statements, unless some, mysterious holism is in play, like we get with quantum entanglement. But broadly speaking, a description of the whole is a conjunction of a description of the parts, and maybe some other stuff to allow for holism. So you would expect a description of the whole to be logically stronger than a description of a part. So you would expect an equivalence of global descriptions to imply a match of local descriptions, because after all, there's less information in the local. And the Gomes doctrine here that the slide was reporting seems to go contrary to that, because we're, as Henrique just said, we've got a global equivalence with a local non-equivalence. But it's not so mysterious, because by the local non-equivalence is shorthand for really insisting on identity of points according to the little open set U we had. So we had
or any threading,
a threading or a transworld correspondence or identification, so that we spoke of as set U in the two models. And because there wasn't isomorphism or isometry mapping one copy of U to the other, it really was true that a scalar field, such as a Kretschmann scalar for geometry or some, a temperature scalar field, would be different on the two. But if the two patches are considered the same local region as the threading scheme invites you to think, it'll be locally non-equivalent, because it's hot on one patch and in the same patch, in the sense of the act, right? On the same patch in the other model, it's cold.
Right.
Yeah,
And whereas,
I hope that helps.
And whereas a drag along, you would always get, even locally, the same state of affairs, because then
you're forcing the word local to follow the isomorphism of the word of the models.
Okay, yeah, no, I guess I find that somewhat helpful. I wonder if it relates to these issues of dualities, where it seems as though the allegedly physically equivalent states of affairs disagree about a certain physical property, such as like the size of a radius. The thing you guys said about hot and cold, I mean, that, yeah, if these two things disagree about the temperature of the patch, but nevertheless, they globally are the same state of affairs, I think I still find that mysterious. But it is very interesting. So thanks.
To put it in even more pedestrian words, it's just saying that because you're helping yourself to this threading relation, the hot patch is no longer in that threaded region, it's just somewhere else. So once you take into account the whole manifold, you will have all the same facts, just the facts have been reshuffled between all the regions.
Oh yeah, I think that's extremely helpful. Thanks, Henrique.
So it's actually less nutty than it sounds, but it's. I think it is a straight up consequence of the threading being rendered with the word something like same patch or it's local. It just has the consequence that a curious sounding consequence that global descriptions are weaker than local ones, because they've thrown away a concern about which point is which.
Yeah. And in particular, in the Weatherall paper, there's a passage in which he says he takes two metrics, G and G prime, as we did, that are related by some diffeomorphism, and but you use the identity of the base set M, and you say G and G prime at P, at the same point P that is identified using threading, not drag along, they're not the same at all. They're physically different. Therefore, the two situations are physically different. You cannot use threading. And I think that's not correct, because although G and G prime are different at P, G and G prime on the whole manifold are the same, are physically the same. So the whole state of affairs is still the same.
I see. So it's almost like, in order for you guys to say that globally the states of affairs on these two like threading related models are the same state of affair, you have to be structuralist, not just about space-time points, but you have to be structuralist about patches of space-time, where you have across the two threading related models different patches of space-time playing the same functional roles.
Sorry, if you this, what you described now, for me, it would be an argument for drag along.
Oh, okay. Oh, interesting. Okay. Yeah, no, I'll have to think more about this. Thanks, guys.
Okay, thank you. Pedro, next.
Thanks, Antonio. Thank you, Jeremy and Enrique, for your talk. I definitely subscribed the idea that basically mathematics doesn't care about its identities. Well, just perhaps I got something wrong, and just to make sure I got it right. I mean, in your schema about threading, what about diachronic identification? Because in your example about Noether's theorem, I mean, this is something about dynamics, but as I get it, I mean, it's basically for a single manifold, in the sense that, okay, we have this manifold and then we have this dynamics, and we get, in this case, Einstein's equation. No, because we've been talking about across walls identification, I mean, with variety of symmetries, isomorphism, and different, and so on. But imagine that basically two manifolds, say, two models of your theory, and instead of just relying on this synchronic identification, where of course, I mean, I realize, I do agree with you that there is something more beyond mere drag along to accommodate for those scenarios. Imagine that in these two models, I mean, you endow some sort of dynamics, and you try to keep track of basically the identities of space-time points, the fields that you have on your manifolds. Do you have any thoughts on how your threading schema, because the usual response would seem to be that, well, okay, for someone that endorses drag along, this is kind of obvious in a sense, but perhaps I should think more about it, but I'm kind of anticipating that something would be needed beyond drag along. So,
okay, so I can,
sure,
yeah. So, in the examples that we gave, I think the idea of diachronicity is not entirely applicable, because we were thinking of the entire manifold, so space-time manifold, and a single geometry. But now we also talked about two metrics and two models that were not isomorphic, and then you cannot help yourself to drag along. And this example would be more like what you have in mind, I think, about two models that represent states of affairs at different times. So they're not the same if the world's not static. If this world's not static, they're different. They're not isomorphic. And then you have to come up with a threading relation, and to say that let's say you're thinking about spatial manifolds in time. So Barber and Bertotti, for example, they have a way of coming up with this threading relationship, which is called best matching. Best matching is essentially a way of trying to identify diachronically or points at points in spatial manifolds at different times. And there are other ways of doing that, but you have to provide a prescription because drag along is not available. And it's
because they're not isomorphic.
Because they're not isomorphic.
Isometric.
And so you have to provide another relationship. And in this case, best matching is one, but in fact,
yeah, actually, as it turns out, I mean, I'm familiar with best matching, so I was wondering whether, okay, if whether you've thought of a different way of, but I mean, it's if best matching is
well, best matching is a particular choice of threading. So there could be, in fact, I mean, this is a separate work, but each notion, there is a way of associating each notion of a perturbative gauge fixing in these types of theory, and this has nothing to do with quantum mechanics or the quantum version of these theories. It's just a notion of gauge fixing that occurs at the linearized level of the theory. There corresponds a notion of best matching for these 3+1 cases, which you'd have in mind. Sorry, here I really indulged in some physics lingo, but yeah, there's a broader notion of threading, depending on the symmetries, there's isomorphisms at play and the type of theory that you have, and yeah, there's a broader notion of how to define threading between non-isomorphic models of any given theory. And there's a way even to relate these to the traditional notion of gauge fixing. But I mean, we can talk about this later. I think this, what I'm describing now goes a little bit beyond the scope of the talk.
Okay, thank you. Fair enough. Thank you very much.
Thank you, Pedro. Tomasz has another question. Please, Tomasz.
Yeah, thank you. Since I've noticed that there are no people queuing for questions so far, so I was thinking perhaps I could follow up a little bit on Josh's question and this issue of the possibility of identifying some subregions by not following this drag along example. Instead, in spite of the fact that you have two models that are isomorphic, but you can still sort of identify one region with the other, which are not, which do not contain the same sort of the same values of fields. So I was wondering, do you think, guys, that perhaps there may be a connection between this suggestion and one particular reply to this famous tower collapse example that I think Gordon Bellot came up with this example in which you have globally a totally symmetric case in which you have several possible evolutions of the system in the future, such that all of them are qualitatively indistinguishable as a whole, but locally they are distinguishable. And so in Gordon's example, this was supposed to be an argument against sophisticated substantivalism, and Joseph Milia in his article gave this response that you should distinguish between local determinism and global determinism, while global determinism can be somehow can be retained, local determinism can be sort of violated. So I'm not sure, but maybe there is an interesting analogy between what you guys are doing here and this distinction by Joseph Milia and others. What do you think about that?
Yeah, I'll let Jeremy, because he's been thinking about this.
Sorry, Thomas, did you say that Joseph Milia is saying that these examples have a kind of retaining a global determinism, but a local determinism must be denied in the cases in the example.
That's right. That's right. Because the whole problem was that, as Gordon presented it, the problem was that our intuition is that if you have the case of a collapsing tower, there is some form of indeterminism here as to in which direction the tower will collapse. But because of the underlying symmetry, globally, any possible evolution of the system taken globally will be qualitatively indistinguishable, will be isomorphic with any other evolution globally. And so for Gordon, that was an argument against identifying isomorphic models or qualitatively indistinguishable models. He says, no, you can't do this because you will lose our intuition that there is some form of indeterminism involved here. And Milia's reply to that was, as far as I remember, was that yes, globally determinism seems to not to be violated, but locally it is violated, and this is enough to support our intuitions.
Yes, thank you. Actually, this is very helpful to me, and I think to Henrique as well. It just so happens that in our little reading group in Cambridge, we were reading Milia, and I was trying to get my mind around it. And I agree with what you said, Thomas. Though he doesn't use the words global and local, he talks about what you call a local determinism must be denied. He says there is a notion of determinism which is sensitive to hexiotistic intuitions, and that notion of determinism must be denied. The idea is you can intellectually specify and accept, in the column example, one direction as against another. That contrast, which direction, is hexiotistic because it is such a symmetric situation. So I agree that I never thought of this. The final slide of today's talk, just to try and wrap up my quick answer, the final slide of today's talk with its idea of a threading, which gives a notion of same patch, capital U, that is broadly hexiotistic. And it is the kind of thing that Milia is what you might call leaning on or appealing to. And of course, I take the punch. I mean, I think Gordon and Joseph both regarded my DM2 of my 1989 as the target of their papers, because my DM2 was not hexiotistic. It was a global determinism in Thomas's jargon today. So thanks very much. I hadn't quite seen the connection between our final slide today and the Milia view. But I was writing a fragment about this, Thomas, about Milia, and I might, if I may, send it to you at some point. Thank you.
Yeah, that would be great. Yeah. Please do. Please send me this. Thank you. Thanks a lot.
Enrique, no, but that's exactly my assessment as well. It's I think they're helping themselves to this. Well, not helping themselves, but they're employing this notion of local differences, and I think that the same kind of indeterminism would arise in general relativity if you were not looking about the universe as a whole, or the entire state of affairs.
Okay, thank you very much. Now, I have another question, which is a metaphysical one. So it's quite clear from the examples that you have drawn, it is the connection between the notion of threading and that of the mathematical formalism from which it takes its motivation. But now, metaphysically speaking, there are a number of questions regarding the characterization of these threading relations that pop up. So the first one that comes to my mind is what is it that makes different threading relations in fact related in some way, so that they belong to the same family? Or did I get it wrong and you do not claim that there is a family of relations called threading, but just a galaxy of unrelated relations, and you just call all of them threading one? So if you could clarify this to me, thank you.
You want to go first?
Well, I can't, so as a matter of mathematical practice, once you call the objects of the base set by a name, P, Q, etc., you already have a map, which is the identity. You already have one of these threading relations. But in fact, in this example where we have two situations that are isomorphic of two metrics, any other diffeomorphism that is not the isometry will also provide you with a threading relation. It will also give you an identity of points that is not, so you don't, it doesn't have to be the identity with which you started. I see nothing special in that I don't want to think of the identity of points as metaphysically robust, but there is something special about a contrasting notion to the drag along when you are considering isomorphic models. And so any other diffeomorphism that is not a drag along can provide such a threading relationship. Of course, you're still helping yourself to the identity of points, even to articulate diffeomorphism and such, but that cannot be helped. And I think it's the strength of the idea is that it doesn't matter that you're using that, that you're helping yourself to that notion of identity. You're still saying any diffeomorphism. So any other reshuffling of labels would have also worked, because any diffeomorphism that I use that is not in the drag along would suffice for all these other uses of threading. I don't know if Jeremy wants to add anything to that.
Actually, no. I think it was very helpful, because I think, Antonio, in a sense, we have had our nose and our eyes rather close to the whole argument literature, but giving one or two talks about it, a question like yours about what is the general landscape is really quite exciting, because once you allow that there are, worthwhile relations which aren't following the arrows of an isomorphism between one model and another, worthwhile relations to think about, you think, well, gosh, is it a galaxy of diverse cases, or are there some natural groupings here? And I mean, to be honest, I don't think we've really mapped it out. But I do think what Henrique said, which I'd never heard before, is a good start. I mean, roughly, if you have a formalism which in any sense uses singular terms for items that will be the topic of your maths, instantiating some pattern, you'll have your little singular terms P and Q. Then this is the whole tradition of set theoretic formulations of theories. You're going to have what we call the identity map on that set. And even if you don't much like set theory, you're going to have something like the identity map. And then once you say but I'll add structure, then you can talk about non-identity maps, and you can follow structure or push forward structure, as a logic person might say. And that's, of course, push forward also in geometry, or pull back. And so there's the contrast there. There's identity map versus drag along. And then there's, of course, apart from full isomorphism, there's preserving a bit less than all postulated structure. So this is the kind of landscape of options, I think. Thanks very much.
No, thank you. That was very helpful. Next, we have a question from Joanna. Please go ahead, Joanna.
Thank you. I would like to ask for the clarification. What's your stance towards sophisticated substantivalism? So should we understand your arguments as being against sophisticated substantivalism, or only against one of its variants, which endorses the drag along as response, while some other variants of sophisticated substantivalism are tenable? Maybe it's a bit terminological question. I don't know.
No,
perhaps depends how do you define.
It's a beautiful question, very astute question. Henrique, you want to go first? Of course, you know, we differ, you know, we're not clones exactly.
No, so the answer is yes. So we are, I am a sophisticated substantivalist, but I think that the drag along is not mandated, and it's not necessary. It's not mathematically mandated. And the original argument, Jim's argument, was supposed to end the debate by invoking this mathematical necessity of you have to use a drag along, otherwise things are not equivalent at all, are not physically equivalent. And this is the example of the metric at the point P that I was giving. And I think that misses the mark. I think things are globally still isomorphic, and that notion is perfectly coherent within sophisticated substantivalism without having to invoke always the drag along, although you could invoke the drag along to explicate a number of situations in which you want to understand better the equivalence. But yeah, so at least from my perspective, yes, I am a sophisticated substantivalist. I think I'm a structuralist in a way, so I think structure is what matters. And but I don't think that the drag along is how you must get to the structure. And I think that's, yeah. Anyways, that's my view. I don't know if we differ in this respect.
I'm joking because, as I think Henrique knows, I'm mostly a sophisticated substantivalist, but a little part of me still wants to be like I was joking with the slide with the word naive. I quite like to be naive. And when I wrote the 1989 paper, I had the background feeling that if you're a substantivalist, put your money where your mouth is, be a straightforward person. If an object is P, then, you know, so what if in another, you know, just bite the bullet and have the indeterminism at a metaphysical level. General relativity doesn't know anything about whether it's P or Q that is clothed with certain geometric and matter field properties. General relativity doesn't know and doesn't care, and physics doesn't know and doesn't care. But that doesn't prevent us metaphysicians making a distinction and pointing out that there's a difference, and thus bite the bullet and have have an indeterminism. But that's quite clearly not sophisticated substantivalism. That is thick-headed traditional substantivalism, and just accept Ehrman and Norton's radical indeterminism and say it's innocuous for the purposes of physics. But I should say, I mean, since Carl, we're so lucky to have Carl here, of course, I mean, Carl, as I understand it, your view is sophisticated substantivalism, your view back in the early 90s in the Journal of Philosophy.
Right, yeah.
Now calls
apparently.
I think the label is from Oliver Pooley.
Right. Well, it was first, no, Ehrman and Bellot put the tag on people like you and me, or you in some moods and me, intending it to be insulting.
Yes.
But we thought that's right. We
right. Sorry, it is actually, yes, it is Bellot and Ehrman who name it. Right. Thank you. Yeah.
Yeah. Yeah. I just wanted to go back to one of the things that Thomas asked about Milia and determinism, and he has also this example of the bald philosophers. Do you remember this, Thomas? And so he wants to convey this idea of indeterminism by having 5 bald philosophers on a circle or something like that, and at some time one of them will grow a hair, and this is supposed to illustrate indeterminism, that the bald philosophers are identical in every respect, and one of them grows a hair. And I think this really relies on this global and local distinction to say that it's indeterminism, because you can have a law of nature that says, if you quantify over the philosophers and you say one of the philosophers will grow a hair, and you don't care which one is which, if you just care that the global state of affairs has one philosopher who has a hair, then there is no breaking of determinism. But if you care which one is which, if you care, if you have these local or hexatistic concerns, then the law itself will have to break the original symmetry. The law itself that a philosopher will grow a hair is no longer, if you don't specify which, every time you choose one, you will be led to a different state of affairs. So yeah, I just occurred to me that this example might also be more, and we have some bald philosophers, nearly. So.
You're right, Henrique. Giovanna, please go ahead.
Yes, it's a continuation. So assuming that you're both sophisticated substantivalists, do you mean by sophisticated substantivalism something more than the assertion that there exist space-time points and that isomorphic models are physically equivalent? Is there something more? Or maybe something else?
Well, you answer. Yeah.
No, I don't think so. But I think you have to specify, there often confusion. The confusion comes from taking isomorphism wrongly. So there is this famous counterexample to Jim's idea, which is Brian Roberts has in one of his response to Jim Weatherall's paper. He has this example where he has a half Minkowski plane. And then he applies a shift to the half Minkowski plane. And now he sees this image of the half Minkowski plane as a subset of the original one. And he says, are these two universes the same? How can they be, since now one is only part of the other? But I think it's wrong because this map is not an isomorphism, because it's not a bijection. If you take the same subset, if you're thinking about threading, if you're taking the same subset so that you can actually compare the image with what it was before, then it's not a bijection, because it's not surjective on the original manifold, right? It's not occupying all the points that it occupied before. And so I think a lot of confusion arises actually from forgetting what isomorphism has to be. And this is why I think it's important to insist on the global aspect of it, as I was mentioning. And yeah, so of course, so just to go back to the Brian Roberts example, and if you just take the drag along, then the drag along is, you're dragging the points with it, it's no longer part of anything, it's just itself. And then they would be isomorphic, but trivially so, as everything under the drag along is. So he has two options. Either he takes, he thinks of threading and thinks of this mapping as being from M to a subset of M, and then it's not a bijection, or he thinks of it as a drag along, but then it is an isomorphism to court, and it's not a subset of anything. And the argument that the argument essentially is mereological, saying that how can a part be the same as the whole? So proof by contradiction doesn't go through. But yes, I agree with you. There are space-time points, and yeah, and isomorphic models over these space-time points.
Okay, Jeremy, do you want to add anything?
No, thank you. I'm just writing notes for our education and improvement of ideas here. It's all good. Thank you, Joanna, for that question. I think for me also, sophisticated substantivalism meant exactly what your question said, which Henrique endorsed.
Okay, thank you very much.